when you have 30 people. Again, the idea is, it's really the same idea as with 5 people, except instead of 5, you have 30 people. You're asking each person when their birthday is, right? That's the experiment. So the total number of possible outcomes is 365 to the 30. I have no idea what that number is. I'm sure it's big. And you want the probability that they're all different. Well, that's what the permutation gives you. The order matters, and clearly we want them all different. Now, to actually understand, to actually get to the birthday problem, the birthday problem actually says what's the probability that at least 2 people will have the same birthday. So it's not quite the same thing as this. It's not quite the same thing as this. In other words, what's the probability that at least one birthday is shared? So at least 2 people are going to have the same birthday. To get to that from here, which we can do, we need this. We can actually get the probability of an event happening at least once. Basically, the idea is, as I wrote over here, the probability of an event happening, of something happening at least once, and the probability that the event never happens, those two events are complements of each other. Not one then the other. And we saw earlier that if you have 2 events that are complement, I think the notation was E and E complement, their probabilities add up to 1. That's really just what I'm using here. Well, you might be thinking, okay, well, why couldn't we just get the event happening at least once directly? Sometimes that can be very, very complicated. Usually, I want to say it doesn't always happen, but as far as I know, finding the probability that an event doesn't happen or never happens is a lot easier than determining the probability an event happens at least once. So in other words, this here is usually a lot easier to find than this. And what's nice is, if we know this, we can get this one easily from this wonderful formula. Now for the birthday problem, what's the probability that in a room of 30 people that there's at least one shared birthday? Well, again, it's really just based on what we did before. We get the probability that no birthdays are shared and subtracted from 1. So I don't think that has to be there. So it's the probability. We get the probability that no birthday is shared, right? We want the probability, though, that there's at least one shared birthday. So we found the probability there are no shared birthdays, which is the complement. We do 1 minus that, and we get our answer. So, it's pretty likely. I mean, it's not guaranteed, but it's pretty likely. So if you're in a room full of 30 people, odds are, well, I shouldn't say odds are, but it's likely that 2 people will share the same birthday. And you could probably guess that the more people there are in the room, the higher the probability is going to go. So, okay, that was fun. Okay. Are there any questions on that? I figured it'd be good to do another example with this probability of at least 1 and 1 minus the probability of never. I figured it'd be good to do that. Maybe I should have done this before the birthday problem. I think it's a little bit easier. But let's assume we're going to deal with tossing a fair-sided coin, 2-sided, so it's heads and tails, consecutively 3 times. So we're tossing a two-sided coin 3 times. And what I did was I made a tree diagram. Again, this is just a good way of getting all the outcomes, right? When the first event, I don't want to say event, the first task would be tossing the coin once, right? You can get heads or tails. Toss the coin again, right? You can get heads or tails. So if we get heads on the first one, if it lands heads up, then the coin could land heads up or tails up the second time. And either time, when we toss it a third time, it's going to land heads up or tails up. We can get all the outcomes here. In other words, we can get the sample space as I have down here. Right? The coin can land up, then heads up, then heads up. Right? It can land heads up, then tails up. Right? So we're listing them all. We go heads up and tails up. That's a possibility. And heads up. It's almost like what you're doing is you're going from the top and you're going down to each of these branches, and each path you take leads you to an outcome. So let me say it again. You're starting at the very top. You want to get down to one of the bottom branches, I guess, so to say. And each path you take is an outcome. So I went down here. Then I went down here. Right? I'm kind of choosing that arbitrarily. I went down here. So I passed through H, H, H. That's an outcome. I went down here. Then I go through here. And here, I went through H, H, and T. That's another outcome. I go to H. I go to T. Right? We took care of this side. Let's go to this side. So H, then T, then H. That's another outcome. And you keep on doing this. Notice there are 8 outcomes. I mean, you kind of expected that from the counting principle, the basic counting rule, excuse me. Right? When you toss the coin, you're tossing it 3 times, and each time there are 2 possibilities. By the basic counting rule, you have 2 times 2 times 2, which is 8. Okay. So what I figured we'd do is this. I mean, we have the sample space, so we can really verify our results. I want to find the probability that the coin lands heads up, exactly 3 times. And the probability that the coin will land heads up at least once. Okay, so again, we have the sample space, so it's a little bit easier. Well, the coin landing heads up exactly 3 times, right? So we want the probability of that happening. Well, if we look at our sample space, there's only one outcome where that occurs. Here. Because of that, the probability would be 1 over 8, as you can see. Now, what about the probability that the coin lands heads up at least once? Well, since we have the sample space, we could just look for all the outcomes where the coin landing heads up occurs at least once. And that's what this is. Right? All these outcomes, as you can see, the coin lands heads up at least once. At least allows more than once. So 3 times is still a possibility. We're not saying exactly once, we're saying at least once. We get 7 out of 8. Again, this event is 3, 6, 7, and there are 8 possibilities altogether. Now, what about the coin never landing, actually, oh, okay, we'll do it here. What we could also do is this. We could also determine the probability of the coin landing heads up is at least one time, okay? Here we go. The coin landing heads up at least once, right? What we could do is determine when that never happens. So when the coin never lands heads up. We could do that. And when does that occur? When each time the coin lands tails up. So we could do that. The coin lands tails up all 3 times, as you can see. And then we do 1 minus that. And how likely does this occur? Let me see, where's the sample space? Back here, right? Well, that's only occurring once. So we found the number of times it never lands heads up, which is 1 out of 8. And then we just do 1 minus that. So basically, I'm just illustrating that rule. That's what I'm trying to get you to see. I mean, we get the same answer. Well, that's good. That's what should happen. Okay? Right. I mean, here it wasn't so bad, but you can imagine, what if we had like, 52, a deck of 52 cards, and we're drawing a card 3 times, right? With or without replacement. Something like that. I would not want to list the sample space. So just an exercise I thought it'd be good to do. But you can see we get the same answer, though. We find the probability that it never lands heads up, and we do 1 minus. Are there any questions? Be right back. Something I just got to do.